Okay, so I talked about, I got to the present with my previous lecture, and now I'm going to focus on perspective and what's ahead of us for the future of this field. So I will recap. So as you notice, I'm trying to recap every time where we got to, so that you get a bit of the full picture, because the reason why, I make a parenthesis, the reason why I take this kind of historical approach is that what happens, what we measure determines which kind of experimental decision we make for the future. So in the case of GPDs, as it's so complex, we need to know what's left to be done. And this determines how we define the experimental program, the setup, the machines that we choose, and so on. So what we have learned so far on GPDs, we have brought a lot of constraints on the imaginary part of H, with the measurements done in class and class 12 and all A as well. And this allowed us to do the tomography of the proton. We also have constraints on the real part of H, mainly by the cross-sections measured in all A. And we saw the importance of the real part of H for the extraction of the D term and the pressure of the proton. The experiments with longitudinally polarized target give us initial constraints on H tilde, but we have new data now just taken, which will give us more information. We saw how important is time-like quantum scattering to extract the real part of H, the D term, and prove the universality of GPD. And NDVCS, it's important to get the E GPD, in particular for the neutron, and also for the separation of the flavor of the GPDs. This is something that I'll come back to today. The proton DVCS on transverse target was only measured by Hermes. I mentioned it in the second lecture yesterday, but it's really important if we want to extract E of the proton. With NDVCS, we get E of the neutron, but if we want to separate the flavor, we need to combine it with E of the proton. We still know nothing about the X dependence of GPDs aside from model assumptions, because as I mentioned yesterday, DVCS only give us the quantum for factors which depend on the variable psi and t, but not on the X variable, which is integrated over. So, and then from DVMP, so far we had only, from pseudoscalar, we had a successful GPD interpretation for the transversity GPD, but for the other meson, we really don't know what's happening in the quark valence region. So we may need to go to higher Q square. So what are the perspectives for the next few years? So there is the experiment on DVCS on transversely polarized proton at class 12, and there are a lot of upgrades that are being discussed here at Jefferson Lab. The upgrade in luminosity for class 12, the introduction of a polarized positron beam for CBAF, and also the doubling of the CBAF beam energy. And at the longer term, in the future, the perspective that everybody is getting excited about is the electron-ion collider. So why do we want to measure transverse spin asymmetry? It's I forgot to put here the dependence of the asymmetry as a function of quantum for factor, but this observable has a very strong sensitivity both on H and E. So E is the one we know the least, so we need to measure this, this observable. However, it's a complicated setup to make, in particular for class. Having a transverse target has a lot of complication. I'll come back in the next slide. So we need to measure it in order to extract E, in particular for the U quark, and we have only data from Hermes at low statistic. This experiment was approved several years ago by the PAC of Jefferson Lab and was defined a high impact experiment. I mean, the experiment that will really bring more knowledge to the field, but it was only conditionally approved because of the technical obstacles in developing a transverse target for class 12. So the situation, it's still challenging for class 12. And there is an experimental problem. So having a transverse target, polarized target, means that you need a magnetic field that has to point in the direction of the polarization of the target that you want, okay? So right now, the way class 12 works is that you have the beam going this way, and you have a solenoid magnet that creates a longitudinal field. And when I say longitudinal, it means that it goes in the direction of the beam. If you want to have a polarized target transverse to the direction of the beam, first of all, you need to get rid of the solenoid magnet. And the solenoid magnet has several reasons why it's there. It's there also because it focuses the Muller electrons that are produced by the beam, and that would create noise in the drift chambers. So if you don't have that and you have a transverse field, you risk to spray a lot of background from the beam all over your detector. So having a transverse target at the beam line and detector level complicates things, because there's going to be the need for what they call a chicane of magnetic fields in order to be able to allow the beam to go through in spite of the transverse field of the target. And on the other hand, technically, it's difficult to produce this polarized target. There was a project that was in R&D stage for a lot of time here at JLab, was this HDI's target that in the end proved not to be able to work in electron beam. It was a kind of polarized target that was used for photo production with class at 6 GeV. But when it was tested in a test beam with electron, the electrons were basically burning down the polarization of the target. So the target polarization couldn't hold with the radiation damage induced by the electron beam. So this project was discontinued, and a new concept, not new concept, but actually a concept that is already used in the other polarized target experiment here at JLab, which is the dynamically polarized NH3, has been brought up as an alternative for the transverse target of class 12. But there are, so it's a good technology that is well known and mastered here by the target group at JLab, but there are some problems. In particular, the magnet that is going to be used is going to kind of limit the acceptance for the particles that we can have. In particular, it's going to prevent the use of the central detector of class 12, where the recoil proton of the VCS can be measured. And here comes the hero that is behind there. So I wanted to embarrass people. So basically, in order to understand if this experiment can run, we need to see if the VCS can be measured even with this limited acceptance, in particular without detecting the recoil proton. So what Juan Sebastian is doing is trying to see if applying machine learning techniques, the background separation from the signal can be achieved even in the E-gamma detection topology. And there are also R&D studies on different possible solutions for target and the magnet. So this experiment is really, from my point of view, the missing piece for to have the full picture, at least for proton VCS. So Juan Sebastian, your work is very precious, and everybody's looking forward to your results. And another thing that is missing, if you think about my summary at the beginning, I said that we still don't know anything about the X dependence of the GPDs, because in DVCS, this X dependence is integrated over. So there is another channel that can be used to circumvent this problem. And this channel is the double DVCS. Double DVCS means that you have the same thing, you have the virtual photon both at the initial and the final state. So your scattered electron produces the virtual photon coupling to the quark, and when it radiates a virtual photon that then decays in a pair of leptons. So with the fact that there is this extra Q square variable added in a final state, it allows to extract the dependence on X. And so basically, when you have this, figure here showing what we access with DVCS asymmetry or cross-section, double DVCS would allow us to cover all this region here in the middle. So all that. So it's an interesting channel from this point of view, but it's also very challenging experimentally. So again, it has a cross-section that is smaller than the one of DVCS. And we need to detect muons in the final state, because if you want to do it, there is also the option of the decay in an electron pair, but then you would have the problem of distinguish which is the scattered electron, which is the decay electron, and there she comes. Why is the cross-section? No.
The energy of the scattered electron will be way more than the energy of those electron pair, right?
It may be overlapping. I mean, so you cannot really tell which one is which. And how do I do it? I shouldn't go there. Okay, sorry.
Even
I like to be close to.
Even in the detectors, won't they be separated well enough?
I mean, they are separated. You can detect as many electrons as you want. But then how do you say, this is the scattered electron, this is the decay one? Okay, so the opening angle of the two could be whatever. It's not really something you can solve experimentally. But with muons in the decay, you're sure. I mean, the initial state, the scattered electron is an electron. The decay of the virtual photon in final state is with muons. So with muons, you would be okay. The problem is that class 12 doesn't have a muon detector as it is. So this is the main complication. Well, but muons transverse all detectors. So you can put an absorber and this sort of stuff that absorb and I'll talk about it in the next slide. There you go. So yeah, so there are, because here we are talking about upgrades, and there is a project of upgrading class 12 in order to be able to measure double DVCS as well as J-psi with the mu plus, mu minus channel. So the idea here is to have an increase of the luminosity of the detector by 2 orders of magnitude, and this would allow to sample the smaller cross sections that you get with double DVCS. And so there are a lot of technical changes that are planned to be done, and I'm not going to go in the detail of all this. There is a letter of intent that was submitted to the PAC a few years ago, and that there is also a similar project that is being defined for the SOLID project. That is a future detector that should be constructed for OLA. And so the double DVCS, in my opinion, would be really the measurement to do if we want to get more model-independent information about GPDs. And then there is the other project that it's a more long-term project because it involves an upgrade and a modification of the CBAF accelerator. It's the development of a polarized positron beam. The way CBAF works now is polarized electrons. So there are several physics cases that push for the need of such a facility at CBAF. So there are different physics that can be done, but GPDs are part of this overall project. So there was a paper that was was more than a paper, it was a collection, a topical issue, a full issue of European Physics Journal A that came out outlining the whole experimental program that could be done if we had the positron beam at JLab. And there was a lot of people, and my group was involved in that as well. And in particular, when it comes to GPDs, there were 2 proposals for the VCS that were submitted a couple of PACs ago here at JLab, and now they've been resubmitted now after having been conditionally approved before. The conditionally approval, it's something that the PAC does whenever it means basically we are very interested in the physics project, but there is no positron beam yet. So come back when things are developing more from the technical point of view. So there had been an experiment making the proof of feasibility of having a polarized positron beam, and this was done a few years ago. And after that, there has been a lot of R&D that is ongoing to try to implement this concept and have it really at the current that we need to run experiment at JLab. So there is a bit of confusion as far as the timeline. This project has been getting more and more support from JLab management, which is something that is very good for us. On the other hand, from the scheduling point of view, it seems like it's going to happen not right away. So there can be a few years, and it may be approaching the time that the EIC will start. So this can create some problem of deciding where to go. But there are a lot of discussions at Jefferson Lab right now. So I just wanted to show you why for DVCS we want to have a positron beam. I mentioned, I don't know if you remember it yesterday, that Hermes was the only experiment that measured beam charge asymmetry using the difference between DVCS with positrons and electrons. And this observable showed to have a strong sensitivity to the real part of H, which again we need for the D-term, for the forces, and so on. So basically, the idea here is to have positron beams here and to measure different kind of beam charge asymmetry, combining or not combining the polarization of the beam. So basically, you get observables that are connected to different combinations of parts of the cross-section, and there is a strong sensitivity to the real part of H. There were proposals and letter of intents both for proton and neutron DVCS using polarized positron beam at class. Here there is a figure showing model predictions for different models for these asymmetries, and the impact of this kind of measurement, if you do GPD fits to the projection of the observables that we could measure, they show that it impacts a lot the uncertainties on the real part of the GPDH. And I've done a similar exercise looking at neutron DVCS, which is my favorite measurement, as you may be figured by now. And the beam charge asymmetry for neutron DVCS has a strong impact on the extraction of the real part of E, which we don't have much constraints so far on. So, so this is a channel that would be potentially really interesting to measure, but it will need this positron beam at Jefferson Lab. So then there are talks about a 22 GeV upgrade for Jefferson Lab, which basically would mean from the DVCS point of view, you see a plot here showing the Q square versus X distribution. The red is the coverage that we have right now. So you see we arrive up to Q squares of about 8 GeV for X equal 0.5. If we were to go at 22 GeV, we would reach Q squares of about 15 GeVs. So there are several advantages, and not only advantages. I mean, personally, I am not hugely convinced about the progress that we would get in DVCS going at such Q squares, because the cross-section drops as a function of Q square, and so it would be more and more challenging. So there has to be necessarily an associated improvement in the luminosity, in the luminosity that the detector can get, so that you can measure smaller cross sections. But it was pointed out that this is something I didn't go in detail much at the beginning, but if we want to apply the handbag leading twist and leading order diagram, we need to have the T transverse momentum, transferred momentum to the proton has to be smaller than Q square. So Q square has to be high enough that you have a small ratio of T over Q square. And basically, if we go to higher energy, you can get that you can reach higher T and still have this limit to hold. And this is interesting if you want to get a good coverage of this distribution of the radial pressure that is connected via Fourier transform to the variable t. So what is said is that we need 22 GeV to cover a sufficient range in T for the extraction of the mechanical properties of the proton. I think that the real motivation for the 22 GeV is beyond the VCS, but is more in DVMP, which is the place where we said that we still don't know what happens when we are at low W and low Q square. So if we go at higher Q square, we may find ourselves still in the valence regime. So that's where we don't know what's going on yet, but with sufficiently high Q square that maybe the handbag diagram could be applied. So this seems to me like the only channel, the only part of the GPD program which would really strongly benefit from an increase in energy. On the other hand, at the longest term future, I guess some of you must be involved in it. There is the electron-ion collider that is supposed to come. I think the expected date is roughly 2034 or something like that, which is fine for your age. It's getting a bit distant for me, but you are the future. So EIC is not only about GPDs and nucleon structure, but there is way more in the physics that can be done. So in particular, one of the main motivations for the EIC is to study saturation. So basically, as I showed you in the first, I think, lecture, there was this different PDFs for the partons, and you have the gluons that have a distribution that goes increases indefinitely with decrease in X. So what needs to be understood is there at some point some moment in which this rise stops, some sort of saturation that happens with gluon matter. So this is something that can be explored by going at lower X by the use of a collider. So another of the purposes, of course, is understanding the partonic structure of nuclear nuclei, which is the goal of the measurement of exclusive reaction that we are talking about now. So understand the spin of the mass of the nucleon, how they emerge from the dynamics of the constituents, do our beloved tomography, in this case, looking at quarks and gluons, while here at Jefferson Lab, we are mainly focused to the valence region, trying to understand the contribution of the orbital momentum to the spin and so on. And then there are also studying hadronization and the nucleon force and many other physics cases can be done at Jefferson Lab, sorry, at the EIC. So, okay, here just reminded, but we talked about it also at the beginning, why it's good to have an electron as a probe. So why do we want an electron-ion collider? If we have a hadron-hadron collision, both the probe and the target have a complex structure. So there are this soft interaction before the collision. The factorization is difficult to apply, and determination of the kinematics is complicated. While if we have a point-like probe without an internal structure, it really probes the structure of the target. So this is why it's important to have an electron-hadron collider. So we need the EIC with high luminosity, different kinds of beam, hadron beam, and different polarization covering a wide kinematic, so that we can explore the gluon-dominated region and the quarks as well, and understand QCD. So as far as the exclusive reaction measurements that we can do with the EIC, so we could still think about measuring the VCS, and then we can have the measurements of vector mesons, such as the JPSI, exclusive electroproduction, which will tell us more. It's a process for which the only possible diagram in terms of GPDs involves gluon exchange. So with this reaction measured at the EIC. There have been some projections made, and this is the kind of distributions that we could have doing a tomography by using the GPDs of the gluon that would be extracted with the measurement of this final state. So there are different, as I said at the beginning, different physics goals for the EIC, and each physics goal has a different requirements in terms of luminosity and the energy. So the kind of physics that we want to do with the GPD is the one that really pushes the requirements in terms of luminosity for the EIC. So as we want exclusive final state, the cross-section is small, and we need to be at high luminosity. So this is one of the challenges that I see for the EIC to carry out the physics that we plan to do to understand the nucleon structure. From the point of view of the kinematic reach for DVCS, you see here a distribution of X versus Q square, and with Jefferson Lab, we are here right now, and 12 GeV is the grid here, and the compass covers the green grid, so going towards smaller X, so more in the C and gluon region. And then you have the EIC for different values of the center of mass energy where we would be measuring. So you see mainly the EIC goes at very, very, very low X, where we said we have the dominance of the C quarks and the gluon. So a few years ago, there was still a debate whether the EIC would be placed here at Jefferson Lab or at Brookhaven. And the final decision was made that the EIC will be at VNL. And basically, it will be reusing part of the existing accelerator that is RIC, and there will be the addition of electron storage ring. And this setup will provide highly polarized electron and proton and ions beam with the center of mass energy between 20 and 100 GeV, and luminosity between 10 to the 33 and 10 to the 34. And this tells you why I was saying that it's challenging to do the measurements that we need to do for exclusive reactions and GPDs. So there is a polarized electron source, injector linear, and in principle, the accelerator could allow to have two interaction points to place two different detectors, although right now the main project is to have one single detector. And the status of the project on the DOE level, there are all these milestones that you have to go through that are the critical decision of the DOE. So there have been already critical decisions 0 and 1, which basically are further levels of approval to give more certainty that the project is going to happen. And the site has been chosen. There are a lot of activities ongoing. There has been a white paper, and the detector was finally decided. And the facility completion, as I said, is in roughly 10 years from now. So the detector of the EIC, the requirements are here. You see the hadron beam comes this way and the electron beam comes this way. There's the collision here, and you have distribution, angular distribution, and different positioning for the detectors. There's going to, I mean, this is going to be a detector similar to the kind of detector you see at CERN, so like a particle physics detector, latest high-tech setups. So there's going to be a vertex detector, central tracker, electron, hadron, and cap trackers, and PID is going to be done by combination of rich and high-resolution detectors, calorimeters, both for electromagnetic showers and the hadron calorimeter. And then there are a lot of developments ongoing for the DIQ readout. And there are also very forward and backward detector. I will come back on that after. So the detector concept that was chosen was this EPIC detector, which is called detector 1. There are still discussions ongoing for a second detector, and there are groups that are discussing on that, but this is the detector concept that came out. As you see here, depending on the colors, there are hadronic calorimeters. There is a solenoid field in the center. First, it was said that for the solenoid, they would recover a magnet from Babar, I think, but I presume that lately they have been changing the plans, and the plans is to have a brand new magnet that is going to be built for that. And there is a set of detectors in which I'm not going to go in details to provide tracking, PID, and calorimeters. So just to come to our interest, that is the measurement of exclusive reactions and in particular DVCS. So if we want to measure DVCS, the kinematics are peculiar. We are going to have an electron and a photon emitted at low angles in this direction, and a proton going at very, very low angles in the other direction. So in order to allow this sort of measurement, in my team, there is an intensive R&D work ongoing, both at the level of the calorimeter that will allow to detect the electron and the photon, the electromagnetic calorimeter. And you see here, again, the future famous scientist, Noemi, who is also working as half part of her PhD on the R&D for the readout of the PW4 calorimeter, lead tungstate calorimeter for the electromagnetic end cap. And in my group, there is also work for the very forward detectors that will allow to detect the protons. In particular, there is work ongoing for the readout. So just wanted to advertise the projects that are ongoing in my group. I want to make a global summary of everything now, because this is basically the last lecture properly defined. Tomorrow, I want to make a tutorial on experimental techniques, because I talked a lot on cross-sections and asymmetries, and I want to give an idea of how you measure them, because that's what you guys may have to do in your career, more than just think about the physical interpretation. But what I wanted to convey, I hope you understood, is that generalized parton distribution are a unique way to understand the structure of the nucleon. They allow us to do this three-dimensional imaging of the nucleon, correlating the transverse position and the longitudinal momentum of the partons. They can give us information on the orbital angular momentum carried by the quarks and its contribution to the total spin of the nucleon, and also giving us information about the pressure distribution in the nucleon. So what has happened is that with the progress on the experimental side, the amount of data that started to come triggered intensive work on the theory level to extract in a model-independent way GPDs from DVCS observables. So this extraction GPDs allowed us to make the tomographic picture of the proton. And now the present is that with Jefferson Lab at 12 GeV, it's really the optimal place where to keep on exploring GPDs in the valence region. And there are several experiments that have been done and are ongoing to measure DVCS and DVMP in 3 out of 4 holes at Jefferson Lab, to extract spatial densities of the quarks, flavor separation of the GPDs, and the quark angular momentum. And there are several upgrades perspective. There is the possibility of positron beam, increasing the luminosity and the energy at JLab. And this paves the road to complete the GPD program in the valence region. And if we want to look at the gluons and see quarks, the plan is to go to the EIC and try to do that. So this ends my 4th lecture. Thank you. Bit early.
There.
Ooh, watch out.
Okay,
Well,
now we have plenty of time for questions. So please. Not spare Silvia.
Oh, you can also, you know. Yes, here he is. What? I repeat question. I go to him so he can I pass under that or it's gonna whistle? Let's see.
For the EAC, is there a reason they don't have a muon like outer layer muon detector? Figured fuels don't need to.
Yeah.
Like, is there a reason they're not? And they're only gonna have a single detector, not like that's the plan. Like, why would they?
Here we go.
Why would they exclude yours? You know,
I don't know why they would exclude that.
I figure. I don't figure.
Yeah, well, you would need the shielding at some place and the detector beyond the shielding to detect the muons. And I guess this is not part of the base design of the EAC right now, of EPIC right now.
Okay.
Detection of muons in the EAC.
Can you repeat the question?
Sure. We can have our EIC expert talk about that. Muon detection. Yes, the question. Yes.
I'm not sure, but the only thing I know is that the space for the detector is super tight.
Mm.
So I think adding any extra thing, like already fitting all of that is super complicated.
Yeah.
I'm not sure if they even have space for a muon detector, but I'm not sure.
Questions? Sorry for that.
I speak too loud already. Don't wake them up.
Yeah. Zoom, people on Zoom.
Oh yeah, people on Zoom. There is one thing on
No,
the
this is
chat. Oh, no.
myself.
Okay, that's you.
Asking them to make questions.
I don't know if they could follow really as well as here on Zoom. It's always frustrating to do this sort of things on Zoom. I'm sorry for them.
Okay. Wait.
We can also discuss tomorrow with the tutorial that
Oh, yes.
hopefully will get some more people engaged. Ciao.
So you mentioned that the EIC would only be able to access low Bjorken X. Is it related to the fact that you've basically like colliding your parton and your lepton at a very high Q squared?
Yeah, well, it's the collider kinematics that covers lower X. It's a kinematics thing. So that's how it is. By the valence, it's here. I mean, here is the place for the valence. Fixed target allows you to cover valence X, and colliders are always at lower X. It comes from kinematics.
Okay, I see.
Right.
That's 10. Okay.
Oh, there she is. What's your name, by the way?
Atira.
Atira. Okay, nice.
I don't think.
Yeah.
Well,
But if people on Zoom.
people on
were
Zoom won't
complaining.
hear you. Yeah.
Oh, yeah.
The previous process that you said that you're really interested about the DD.
Yeah.
That's going to be after the upgrade at Jena, right?
No, that is independent because for that, and I'm happy you asked me this because I like that. Sorry, where is the thingy? I go back this way. Because for that, what we need, it's an upgrade only at the detector level. Where did I put it? Here, yes, here. So we have never measured it. So the current energy, 12 GeV is fine for measuring this, but we need to revamp the detector. So if we want to measure it, we need the muon detector of which he was talking about before, which we don't have in the current class 12, and we need to increase the luminosity. And to increase the luminosity, right now, the limiting factor of class 12 is the drift chambers that they cannot run at too high current because they get noise. So you have to change the tracking system and you need to include a muon detector. So at the same time, it will be a completely different setup, which may not allow measurements of other final state. So it's a decision that implies a complete change of the detector, but for a reaction that has strong potential. So I think it's worth it. But it's something that has been already, I mean, there is a R&D going for the tracking. So it's not it's not something linked to the major management decision of the lab. It's happening really at the detector level. So I think it's, of all the upgrades, is the one that should happen more. Yeah. I would say so. I would hope so. I would hope that this could happen around 28 or so. I mean, hopefully. The EIC, I mean, the EIC is 2034, but that's for the starting of taking data, commissioning, and so on. So I wouldn't expect the data to come out before 36 or 37, frankly. No, I mean, knowing how things go with the stuff. You have a date and then it starts to sleep. So I think it's very important that JLab provides an alternative short-term plan, because students like you cannot just work on something that has not happened yet. You need the data to work on. I mean, I don't like to give only simulations to students to do. You need to have real data, and you can get interesting physics here at JLab. So you can already do it with the JLab not upgrade. There are a lot of experiments about to come even without upgrades. This is, among the upgrades, is one of the most interesting for GPDs, I would say, because it's never been measured and gives more information. Thank you.
Well, if you don't have any more questions.
But we can have a tutorial tomorrow. With the tutorial, hopefully we'll have more exchanges, more kind of low-level experimental stuff, so the theorists will all be disgusted. But maybe it gives you an idea, because, you know, you see here, all I showed were plots of the final result, and behind there is a huge amount of works. Here, years of work, and it's usually done by students. So I thought it would be nice to show, at least from the perspective of what we do in class, what kind of work you need to do, and possibilities and options and so on. Anyway, thank you so much.
No, thank you.
And see you tomorrow.